Hi everyone, in this video I will show you how to implement a water solubility prediction web app from scratch. So at the end of the tutorial, this is the web app that we want to develop using Streamlit. So the web app has a sidebar over here and there is also a main page. The main page is for information purpose. It gives what solubility is. This is a test data. This gives information about web app as well as the model. What is important for solubility prediction is the sidebar. So in the sidebar there is an input box, this input box. The user can enter one or more smiles. The smiles should be separated by comma. Say for instance, if I add another molecule, right? So I can say 1, 2, 3, 4, 5. So once the user enters the smiles representations, press enter to see the results. So the model will give back the predicted solubilities as well as the smiles in table form like this, or it also provides a CSV file that can be downloaded here. Okay, so this is how it works using just entering smiles. The other thing that the user can do is it can also accept many smiles. In that case, file should be in CSV file. The user can drag and drop the file. Say for instance, if I drag and drop it in this area, so the file will be uploaded. Now the file is uploaded. Once the file is uploaded, the user should be able to click on this button, predict log S of molecules. So if the user clicks on this button, what will happen is web app or the model will calculate the corresponding solubility values and it will display a table on this area. Okay, so these are the smile representations. These are the solubilities. It also provides the CSV file that can be downloaded over here. Okay, so the user can download the file. So this is how it works. In the first part, we'll follow these 7 steps. In the first step, we'll get the solubility data, and then we'll do data cleaning. We'll clean the data. In the second step, we'll generate molecular descriptors, because these molecular descriptors will be used as input features for the molecules. And then we will split the compounds for training and test set. In the fourth step, from 42 machine learning models, we'll select the one that best fits to this data. That is the fourth step. In the fifth step, we'll fine-tune the selected model. We'll find best parameters for the model, the selected model, and we'll use that model for the test data. Finally, we will save the model and the standard scaler that we'll be using for future use for new data. So that's the first part. The second part, we'll use this saved model and deploy it into the cloud. So that we'll be doing next. This is the first part. So if you don't know much about solubility, I'll give you a brief introduction about that. Before I define solubility, let me discuss a little bit about solid, solvent, and solution. Solvent is usually found in larger amount. The solvent dissolves a solute. The solute is usually the smaller amount, and solvent usually determines the physical state of the solution. If the solute dissolves in a solvent, in that case you'll get a solution. A solution is a homogeneous mixture. That's very important. A solution is a mixture. Counting the dissolution process as a 3-step process. The first step, the solvent particles need to be separated. So that is an energy requiring process. It is called endothermic. So you need to separate them just like this. So that means you need to overcome the attractive forces between these solvent-solvent particles. Similarly, in the second case for the solids, you have to separate the solid-solid particle interaction. In the third step, they should mix. When they mix, the solid particles will interact with the solvent particles. In the third step, which is a mixing process, energy is released, which is an exothermic process. Step 1 and step 2 are usually endothermic processes, because in order to separate these particle interactions, you need to apply energy. But the third step, which is mixing part, this one, the third step, it releases energy. That is an exothermic process. The heat of solution is the sum of these three steps: step 1, step 2, and step 3. This is known as a heat of solution. This heat of solution could be either endothermic or exothermic, which means the enthalpy of solution is less than 0, means the process is exothermic. It releases energy to the surrounding. Enthalpy of solution is greater than 0. That is an endothermic process. So you need to supply energy to dissolve more of the solids in this case. Another point I want to discuss is a saturated solution. A solution, I would say, is that a solution is a homogeneous mixture. So a saturated solution is a solution that dissolves the maximum amount of solids. If you add more of the solids, you will not see any further dissolution of solids. So that kind of solution is a saturated solution. Let's see the definition of solubility. Solubility is defined as the maximum amount of solids that dissolve in a given amount of solvent to form a saturated solution at a specified temperature. This temperature is usually a room temperature. So solubility is usually affected by temperature. So you need to specify temperature. Another concept that we need to know about solubility is the like dissolves like principle, which means generally polar compounds are soluble in polar solvents. Water is a polar solvent. Polar compounds are soluble in water, and also ionic compounds are also soluble in water. So that's the idea of like dissolves like. Non-polar compounds are also soluble in non-polar solvents. Those having similar intermolecular forces of attractions are generally more likely to dissolve each other. So that's the idea of like dissolves like. Water solubility is an important property in drug discovery because it affects bioavailability, which is the extent to which a drug can be absorbed and reach its target site. If the drug is not soluble in water, even you cannot do any biological assay. So water solubility is a very important property. In general, this implies that molecular structure of a compound can significantly influence its solubility. So if you have a molecule and if you put a polar group on that molecule, which means you are increasing water solubility. If you put a non-polar group to the molecule, obviously you will decrease the solubility of the compound in water. These 200 molecular descriptors are the numerical representation of a molecular structure. We use them as an input feature to predict aqueous solubility. So that's the most important thing. So what we'll do is we'll take smiles of compounds and then we'll generate their R-kit molecular descriptors. There are 200 R-kit molecular descriptors. We'll generate that. And using a machine learning model, we'll predict their aqueous solubility. So the machine learning model is basically maps these molecular descriptors to aqueous solubility. That's what it will be doing. Okay. So the general idea in using these machine learning models is that the structure of the molecule is directly related to its physicochemical properties. That's why we are using these machine learning models to map molecular structure to its property. Okay, so that's what we'll be doing. So we'll use a machine learning model to predict the aqueous solubility of organic compounds. Especially for this particular case, we'll try to predict drug-like molecules. That's what we'll be doing. So the first part, we need to import these libraries. This NumPy, Pandas, Matplotlib, scikit-learn libraries, lazy predict. This is very important. It will help us to select the best model from 42 machine learning models, and also the RDKit libraries. So as usual, to run the cell, you need to press Shift plus Enter. We imported all these libraries. So the first thing is you need to get data. You need to get data. So these smile strings were obtained from a publication. This is a publication. The data was obtained from this publication. There is also an excellent blog post that you may need to read about aqueous solubility, which is written by Pat Walters. So I strongly recommend you to read his blog post. So I got this CSV file from the publication. So let's import it. Let's see the shape. So we have 9,956 rows and 6 columns. Okay, let's see the first 5 rows. If you look at the first 5 rows, the first column contains compound ID, inch key, smile strings, log S, log P, molecular weight. So in our case, we only need smiles and log S values. First, let's see if there are none values or null values. If there are none values for smile strings, for smiles column, we need to check that, right? So how do you do that? We have to use data smiles. This is a smiles column. Is null. We'll check if there are none values, and then we can sum the number of none values using sum. So if I run this, there are 13 rows that do not have smile strings. So that's the make. So we need to delete this or drop these rows using drop NA. So this is the data. So if you say drop NA in place true, we'll drop all these 13 rows. Okay, let's see the data. Yes, we have 9,943. If you remember, we had 9,956. So we removed these 13 rows. Okay, this is our data. The next thing we need to see is if there are outliers. We need to remove outliers. Let's use a histogram to see the distribution of the solubility values. It looks like it follows a kind of normal curve, but it is skewed to the left. Okay, this is negative skew. If you use box plot, we can easily identify the outliers. So let's see a box plot. These values are outliers. We'll drop these outliers. To filter outliers, we need to filter those having solubility values between minus 7.5 and 1.7. So if you filter that, we can remove these outliers. So this is a histogram. It looks like kind of normal curve. In fact, very close, not perfect, but very close to a normal curve. If you use a box plot now, we don't have these outliers, so this is a kind of clean. So how many compounds do we have now? We have 9,648. So initially we have how many? We have 9,943. Okay, the number is kind of decreasing because we removed the outliers. The next thing we need to check is, especially if you are working with the smile strings, you need to make sure that you have canonical smiles. Otherwise, you'll have a bunch of duplicate smiles, and that will complicate your analysis. So this is a function that helps us to generate canonical smiles. It's just a single line of code basically. Let's pass the smiles column to the function. This is our function, right? So this will give us canonical smiles, and then we need to replace the smiles column with canonical smiles. That's what I'm doing here. And the last step, we need to see if there are duplicate smiles. That is the sub line. So now let's run this cell and see if there are duplicates. Yeah, there are 6 smiles that have duplicates. Let's see what these duplicates are. Let's filter them from the data set. So these are the duplicates. There are 12 structures, which means these 2 are duplicates. Obviously, the last one, if you look at this one, they are duplicates. So we don't want duplicates. We need unique smiles. So what we will do is we will drop duplicates. We'll keep only one, the first instance, and we'll drop the other instance of that smile. Now we don't have any duplicates. The duplicates are removed, so the number is 9,642 compounds. The next step is about the test data. For the test data, we'll use the 100 drug-like compounds. The solubility of these compounds were determined in one lab using a very accurate solubility experiment. Okay, so these are the references. So this is a publication. Read this publication for further information. We can read about this one, but the data was directly obtained from this website. Okay, it was downloaded from this website. So there are 100 drug-like compounds. So we'll use this for the test set. So we'll use this for the test set. And then if you look at the data, these are the compounds. There are 100 compounds actually. There are 100 compounds. You can take a look at them. So there are 100 compounds. This is smile strings. These are the solubilities of these compounds. So this, as I said, the solubility data is obtained using a very accurate experiment. So the experimental error is very small. For the other compounds, these are collected from the literature. So the experimental error should be higher compared to these 100 compounds. So we'll use them as a training, but the test data will use the more accurate data points, or the compounds that have very accurate solubility data. Just need to generate canonical smile, and then we'll replace the smiles column with canonical smiles, and then see if there are any duplicates. I'm pretty sure there is no duplicates, but let's see. Yeah, there is no duplicates. The other thing that we need to do is we need to make sure that these test set compounds are removed from the training set. This is our training set. We need to remove them if they are present in this list. So the first thing, we need to store these smile values into this list. So this data clean final contains compounds for the training set, and it does not contain any of the test set. So we have 93 compounds which are present in the training set, but in this case we just removed them from the training set. This is the training set. So if you look at the data, we have 9,549 compounds. If you remember, before removing the test data, we have 9,642. So 93 compounds are removed from the data. That's why the number is decreased to 9,549. Now this is clean, ready for the training set. Then we need to do similar filter for the test set, so that solubility should be greater than minus 7.5 and less than 1.7. They need to have the training and the test set should have the same scale. Basically, we need to remove our outliers if there are here. 98 compounds are within this range. The next thing is we need to generate molecular descriptors, right? We can generate RDK descriptors using this function. I already explained how this function works in another video, so you can watch that video to understand how this code works. But for this purpose, I simply run the function to calculate molecular descriptors for the training data. So there are 200 molecular descriptors that are available in RDKits. I'm just calculating that one. It may take about 2 minutes. I'll pause the video and I'll come back when it is done. Okay, it's done now. So we calculated these 200 molecular descriptors for each molecule. Okay. So if you look at the shape, these are the number of compounds we have. These are the number of features. These are the number of columns, right? So we have 200 columns or 200 molecular descriptors. Now let's split the compounds for training and validation set using the train test split from scikit-learn. Okay, now we splitted them, and then we need to use standard scalar. Now let's use this lazy regressor, which means we are training 42 machine learning models using this single line of code, which is really very convenient. It may take about 2 minutes, so I will pause the video and I'll come back again when it is done. Okay, now it is done. Let's see the top 3 models. So as you can see here, light GBM regressor is the best one. It has a root mean square error of 0.74 and the coefficient of determination is 0.86. So this one is the best model. The next best is Hist gradient boosting regressor, and the third one is extra trace regressor. So these are the top 3 models. The other advantage of light GBM regressor is the processing time is really fast. The others take longer time, but light GBM regressor is really the fastest compared to the other 2. If you want to see all the other machine learning models, see how they look like. Okay, so these are all the machine learning models available in this lazy regressor. Some of the data are really weird, but anyways, the best model is light GBM regressor. So now let's keep that into 3. Okay. All right, so the next thing I did was fine-tuning this light GBM regressor. I used a grid search to find the best maximum depths, number of estimators, and learning rate. So what I got was the best value was learning rate 0.04, maximum depths 26, and number of estimators 1,150. So I got this one. Usually it takes a longer time, so I don't want to run them over here. But if you want, you can try that one. So using these best parameters, we can retrain the light GBM regressor and then predict the validation values. Let's see how it looks like. We are doing prediction of the validation set here. So this is just to plot the root mean square error and coefficient of determination. So I wrote this function to generate a plot. If I pass the validation value and the predicted value. So this is a predicted value which is obtained from the model. So this is the actual value of the solubility values of the 10% validation data. So now let's see how it looks like. Let's see the graph. Oh, I didn't run this one, so I need to run this first and then this second. Okay, so you can see that the root mean square error for the validation set is 0.72 and the coefficient of determination is 0.86. Okay, so it looks good. There are some noisy data, but overall it looks okay. Now let's use the test data to predict the solubility of the test compounds using this model, okay, optimized model. First, let's calculate R-reduced molecular descriptors. We simply pass the smile strings, so we can get the molecular descriptors using that function. Okay, it doesn't take long because only 100 compounds. We need to transform the descriptors so that you can get the scaled value. Once you get the scaled value, we can use the model to predict solubility. This is why test prediction. For the prediction, let's see. And then let's plot using this function, using this plotting function. If you pass, this is experimental solubility, and this is a predicted one using the model. And let's see how it looks like. Yeah, it's able to capture, I think, the patterns, but kind of a little bit noisy. The last step that you need to do is we need to save the model and the standard scalar for deploying it in the cloud. So I need to uncomment this one. Okay. So you need to use Pickle for that purpose. Import Pickle, and then this is the model that you are saving, and this is actual model that we used here. This is a standard scalar. So we are just saving it as a Pickle file. Okay. Now we saved our model, so we can use this model to predict the solubility of new compounds. We need to deploy this. So finally, we'll deploy this model to the cloud so that anyone who has internet access can use it. So we'll deploy this model to the Streamlit cloud in the next video. One last thing that I want to tell you is that try to repeat what I did. I think the best way to learn is you need to practice it. There's a practice problem for that. Instead of what I did with light GBM regressor here. So try to use a hist gradient boosting regressor and apply all the procedures that we did so that you can have a better understanding of how to train a machine learning model. With that, this is all for today. I'll see you with another video. If you like this video, please subscribe the channel. Thank you.